Hi everyone. In this set of lectures, we'll be looking at concepts of recursion and dynamic programming. And in this first lecture of this series, we'll look at solving the Fibonacci sequence or generating the Fibonacci sequence using recursion. We'll be doing simple recursion and then we'll try to optimize it through a concept called memoization. So to start off, let's look at what the Fibonacci sequence is to remind everyone. So I've written down an example here, but essentially the Fibonacci sequence is defined here. And what this says is that the Fibonacci sequence at the ith element is equivalent to the sum of the previous two elements. So it's simple as that. And then the first two elements are defined for us. So there's 0 and 1. And the third element, when you try to calculate it, you'll see that it's 0 plus 1. The fourth element is 1 plus 1. The fifth element is 1 plus 2. The sixth element is 2 plus 3, and so on. So yeah, this is an important definition of the Fibonacci sequence. And if anyone knows anything about recursion, you can see why this is very commonly used to study recursion, because you can very easily define the recurrence and define how you can find any particular value of the Fibonacci sequence um, as sort of defined by subproblems or sum of previous values of the Fibonacci sequence. So in general terms, recursion, if we talk about recursion, it's basically you're trying to call the function within that function, and call it in a way that you're calling it with a smaller problem than the original problem, and then you keep calling that function with smaller and smaller definition of the problem until you hit a base case, and the base case is well defined. In our case, the base case is well defined with 0 and 1. So I think enough of the theory. I think we can get into actually programming here. So yeah, let's call our function fib1, and any Fibonacci sequence function, or most of them, are basically structured where you have a function with one argument, and that argument is going to tell you which element of the Fibonacci sequence you want to return. So we'll call that argument n. That's our one parameter for the function. And then we can define, with any recursion, you want to start by defining your base cases. So if n equals 1, then you want to return 0. And if n equals 2, return 1. So those are our base cases. And then if it's neither of these, then you want to return the sum of the previous two values of the Fibonacci sequence. The way to do that is just return fib1 n minus 1 plus fib1 n minus 2. Okay, so that is about all you need for the Fibonacci sequence. Let's try it out. Let's try to print the sixth element, which should be 5 in our case. So sixth element of the Fibonacci sequence is 1, and we'll give it 6. So let's run this. And it is indeed 5. We can try another one. Let's say it's the ninth element, which should be 21. and it is indeed 21. Okay, so this is pretty simple, right? Like you're just calling your function within the function, and you call it with a smaller problem than the original problem. So your original problem was like, let's suppose 9, you call it with 8 plus 7, and then when you call it with 8, it will come back here, and then it will call it with 7 and 6, and then keep going until you hit one of these base cases, and those base cases are well defined. So, and then it builds up from the base cases until you get to your required um, value. So we can do a quick example of this. So let's suppose I want to capture, or I want to calculate Fibonacci sequence 5, right? So this value. Now, internally, what this function will do is it will start with fib 1 5. It will go through here. Of course, n will be 5, so we'll come here, and it will want to calculate 4 plus 3, right? Fibonacci sequence, the fourth element plus third element. And then then it will try to evaluate the fourth element, so that will be equal to fib 1 3 plus fib 1 2, and then it will try to calculate fib 1 3, so fib 1 3, and it's very simple to understand this if you draw out a tree, but I'm just doing it here. 2 plus fib 1 1. Now you've hit the base case here, so we know that n equals to 2 you return a 1, and n equals to 1 you return a 0, so this will equate to 1. So this 1 gets transferred here. So now this is 1, and then this is also a base case, which equates to 1. So this is a 2, and then this 2 comes here. So you'll have 2 plus fib 1 3, and at this point, it'll need to calculate fib 1 3 again. So it will do the calculation for fib 1 3 again, which is equivalent to fib 1 2 plus fib 1 1, which is just 1. Okay, so that will equal to 3. So your answer becomes 3, which is our eventual answer. Now, this, hopefully some of you might have caught on to this. The problem with this simple recursion method is that, for example, let's look at fib 1 3, right? So you need to calculate fib 1 3 once here, right? But you also need to calculate fib 1 3 again in order to calculate fib 1 4. So you end up having to evaluate fib 1 3 twice. Similarly, you have to evaluate fib 1 2 like 3 times. And granted, it's a base case in this case, but as you get more complicated problems, you'll have more of these subproblems that you have to evaluate multiple times, even though you've solved them before. So that's what makes simple recursion not so efficient, because you do have to keep reevaluating subproblems that you've already solved. And the way to solve that, we'll discuss that later, is memoization, where it's an optimization technique where if you've solved the subproblem, you'll save it somewhere. And so if we talk a bit about the how long it takes to run, because we did say it's not very efficient. So to understand that, if we look at this code here, this line runs O of 1, big O of 1. This line also big O of 1. And then each of these lines, each of these function calls should also be big O of 1. So all of these evaluations are big O of 1, but if you do end up drawing out a tree of how this works, or if we just look at this, right? So we wanted to do fib of 5. So you start with fib of 5 at the top, and then you split it into fib of 4 and fib of 3. So you have 2 branches, and then each of these fib 4, fib of 3 will have 2 more branches. So the first level had 2 branches, the second level has 4 branches, and then each of those branches will also have 2. So you can see with each level you're exponentially increasing the number of branches, and that's why the time complexity um, of simple recursion is with the Fibonacci sequence is big O of 2 to the power n. So obviously not very efficient, and we don't notice it too much here because we were doing a very small value, but as you get to higher values of the Fibonacci sequence, or when you're actually solving more complicated problems with simple recursion, you will definitely see that it's not very fast compared to something like recursion with memoization, or even if you use dynamic programming. Both of those are much more optimized. So yeah, definitely not the most optimized, but it's important to learn this concept because it is used pretty often along with optimization techniques. And you can see like it's very clean in terms of the code. Not much code has to be written with techniques like this. So that's about it for this video. If you guys have any questions, put them in the comment section, and I will see you in the next video where we'll discuss the optimized version of this implementation with memoization. All right, thank you guys.